I've made a lot of work coils, as you can see, and I want to pass on some general comments about coil making. So this video summarizes my experience in making coils for the 1000 watt, 1800 watt, and 2500 watt, 12 to 48 volt ZVS induction heaters that are for sale by many vendors. I will put links to one key web page and several relevant YouTube videos of mine into the description below. So what is the point of this video? I want to make it easier for folks to design and make induction heating coils that work well for their particular application with a minimum of guesswork while not exceeding the power limits of their induction heater circuits. Yes, I know that people fill the tubes with sand, salt, or ice to keep the tube from collapsing while they're bending it, and they go to some lengths to tightly seal the ends of the tubing before bending to make that process effective. But I just don't want all the mess that goes along with those methods. You will see that we can make good coils with inside diameters down to about 1 1/8 inches without all that extra work. For really small inside diameter coils, one can use smaller diameter tubing. Recently, for instance, I successfully made a 5/8 inch inside diameter coil using 1/8 inch diameter tubing. At first, I was concerned that the smaller tubing, such as the 1/8 inch OD tubing that I use for a Cartridge annealing coil, would limit the water flow too much for cooling, but that didn't appear to be a problem, at least not on the 1000 watt unit. I have accumulated and tested several commercial tools for the bending of copper tubing. Most of them basically work okay for making 90 degree to 180 degree bends, but all have important limitations when it comes to making a solenoid coil in particular. Even with these tools, back bending to get the coil leads to go the right way can be kind of tricky. This would be a back bend where we've got to bend it this direction and then back that direction in order to get it to fit on the induction heater PC board. So to begin with, here's a set of 4 springs. And these springs are used by simply selecting the one for the right tubing, stick the tube in there, and then bend the spring. And the idea is that the spring keeps the tubing from kinking. So these springs work okay for bends that aren't too sharp. But if you do make a sharp bend, you may not be able to get the tubing out. Don't ask me how I know. But they are useless for making a coil. Now, none of the following commercially available tools will make bends with IDs smaller than their bender die, which you'll see in a minute. The die inside diameters vary from about 1 1/4 inch to about 1 3/4 inches on these tools that I'll be explaining in a minute. We can make smaller coils than that with a simple cylindrical mandrel anyway, which I'll get to later. Some less expensive tools require the user to do a lot of guesswork to make multiple bends in exact locations, while some of the more expensive tools have gauging attachments to help with this issue. And regardless of which tool you might use, I recommend strongly practicing a bit before committing to your first real has to be just right coil. This is a cast aluminum one-piece bender. It's simple to use, but the groove in this particular one is too big for 1/4 inch tubing. There are many sizes available. This fixed device has multiple bending dies with a fixed handle and a single tubing support. It is simple to use, but the tubing on the other side of the bending die needs to be kept from bending until it is close to the die. In other words, if you put the tubing through the die here, the support keeps it from bending on this side, but if you grab way out here and pull it around, you may create a kink if you allow the tubing to bend very far away from the die. I don't know what else to call this but a pair of pliers. And it has 2 outboard rollers. And it comes with 2 bending dies. And just to back up a little bit, looking at the instructions for this one, you can see, I hope you can see, that the user has allowed the tubing to start bending way out here. And this is a good way to get a kink in the tube. You really need to support the tube and not allow it to bend until it gets right to that roller right there. And it may work out okay with dies this big, but when you try to go smaller, this gets to be the place where a kink is going to happen. And you need to avoid that by coming up with a way to stop that tubing from bending until it gets right close to the bending die itself. And I also want to note that, interestingly, with this die, the instructions are absolutely terrible. But these 2 dies will actually make 4 different size bends. I don't know if you can see it very well, but half of this die is one ID and the other half is a different ID. You can see the kind of a little notch when you go from one to the other. The bending die that's mounted on this tool has 2 different size bending dies, also half and half. And I've got this one set for 1/4, and I have to set it up right so that that bending die matches up with the 2 rollers. Here's another pair of bending pliers with 2 outboard rollers and movable bending dies that align with those rollers. The bending dies are only half a circle. So it may be possible to wind a solenoid coil with some careful planning if you can get the coil to kind of spread off the ends as you go. But as I have said before, we can make coils smaller than these dies with a simple cylindrical mandrel. Here's yet another set of bending pliers. This has some compound movement to it, and it comes with measurement gauges. It is probably the best bender designed for making accurately located bends from 0 degrees to about 180 degrees. But again, it can't make the smaller coils. Now let's take a look at some of the homemade mandrels and things that I usually use for bending work coils for ZVS induction heaters. Here's a large mandrel with 2 grooves. This type of fixture is used to make coils with IDs down to about 7/8 of an inch ID, or maybe a bit less. This, like the other 2 that I'll be showing you, is still a work in progress. It has a bending ID of 1¼ inch down in the slots here. This smaller mandrel has only 1 groove and a tapped hole in the end. It has a bending ID of 5/8 of an inch. Note that I have milled flats on it on one end so I can firmly clamp it vertically into a vise, so at least one thing is an immovable object when I'm bending the coil. I have also drilled and tapped the die end so I can someday fit a tubing support lever. So this is just a test, and I haven't even tried making a real coil on it. I've just tried doing a couple of little initial bends. But the idea of the taper here is so that I hopefully can learn how to just keep going and bending and bending and bending and have my coil just scroll right off the end if I need one that's that small. So this would have a 3/4 inch ID, and I'll get at it one of these days. I've made it out of hard maple, but I don't know how well it will hold up in coil making. In a previous video, I showed how I extend coil tubing without having to use hardware store fittings. Here's the homemade swage I use to make a bell on the end of one piece of the tubing. That way I can slip the swaged end over the existing tube and soft solder it in place. Tools to open up and deburr the tubing after cutting. If you've used a regular tubing cutter, you know that you'll create a burr on the end of the tube, and that particularly if you're going to swage that tubing, you've got to get rid of that burr. There are several ways to do this. This is one brand of deburring tool that machinists often use, and this works pretty well. But just selecting a drill bit of the proper size that you know will fit inside a deburred tube works a lot better with a hand electric drill. And then once you've drilled it out or even used this tool, then I kind of finish up the edge with a fine file just so there are no tiny little burrs left. As I said previously, for coil IDs smaller than about 1 1/8 inch, I use my homemade fixtures for coils with IDs down to about 3/4 of an inch, but it is difficult to do without kinking the tubing. If you need coils with these smaller IDs on a regular basis, I recommend using 3/16 OD tubing or even 1/8 inch OD tubing. Even with these smaller tubes, I still use the 1/4 inch fittings. I simply bush the smaller tubing to fit the 1/4 inch tubing so I can use my standard compression fitting connectors. So to go from the 1/8 inch to the 1/4 inch, I use a piece of the 3/16 inch tubing, a short piece. I don't know if you can even see it in my hand here. And slip that over the 1/8 inch tubing, and then slip the 1/8 inch tubing onto the 1/4 inch tubing with flux all cleaned up and fluxed, and put the two together and then soft solder them in place. For the 3/16 inch tubing to 1/4 inch tubing, of course, that's already the right dimension, so I can slip the 3/16 after it's been deburred directly into the 1/4 inch tubing and solder it together. Here is an example of the 1/8 inch tubing connected up so that it'll go right onto the induction heater. And again, it's probably hard to see, but the little bushings, the little in-between bushings of the 3/16 are right in there. Sometimes when bending a coil, you get some kinking anyway. And maybe you can see that here where things look kind of beat up, but this is where I kinked the tube pretty badly. But if you do kink a tube while you're just starting a bend, you can often open it back up by just gently hammering on the high part of the bump of the kink on a hard with the tubing on a hard surface with a light hammer. Just a lot of little blows, not heavy blows, and it may not look pretty, but you can certainly open it up so that the cooling water can flow through it significantly. And as I've said before, making tight back bends to get the coil ends to properly connect to the heater are the hardest part of coil making for me. That's where the commercial benders can be very helpful. And again, although I've said it before, I've not yet found a commercial bending tool that can produce 360-degree bends, which means I can't use them to make complete solenoid type coils. I've just simply cut off a 6-inch long piece of 1 1/8" just solid steel bar, could be anything. And I milled a couple of slots here so that it will fit and hold well in the vise while I make the coil. Now let's make a 7-turn, 1 1/8" diameter coil using just a cylindrical mandrel, as I've mentioned previously. I'm going to have to wind this coil in a clockwise manner starting from the bottom up so that the input of the coil here matches the incoming water flow from the induction heater. I checked that out before I decided how to do this. For this coil, I'm just simply going to try one of my benders here that I've talked about. I just need a 90-degree bend right here. It's about 90 degrees, which gets me set up for the input to my induction heater, and also traps the incoming end of the coil here in the vise so that that can't turn. So now I'm just going to wind the coil. And I'm pulling on the coil as close as I can get to the mandrel so that I don't kink the coil as I go. One, two, three, four, five, six, seven, and I've got a little bit of spacing in between the coils, so I don't have to overbend it by too much. I'm straightening out several inches of coil here. So that I can get my cutter on here. I'm going to leave myself plenty of extra room. Well, I cut that off. And here's my new coil. Now I will have to make some adjustments here to bend this to get both tubes going the right direction. But this again, this will be the incoming side or the bottom of the coil, and this I will adjust to be the top or outgoing side. Many incremental sizes of this tubing are considered to be telescoping. This means that the next larger size just barely slips over the size just below it, as you saw in a previous scene. This feature makes it easy to join differing diameters with soft solder. So here's just kind of a word about soldering. Be sure to clean the joints carefully before soldering so all surfaces to be joined are bright and shiny. And really, even shining them up and then waiting a few hours can cause some oxidation. So try to be ready to do your soldering right away after you clean things up. Rosin core flux instead of acid core flux has worked out well for me. I'm just concerned about acids hanging around the coil and what have you, and the rosin core flux cleans up very nicely with isopropyl alcohol, or just about any kind of alcohol. I always use compression fittings, but flare fittings are very common and work well too. It's just that the flare fittings require an extra step to flare the ends of the tube, which can introduce a possibility for a leak if you're not doing it correctly. Most ZVS induction heaters that I have purchased arrive with metric sized coil tubing, usually 5 millimeters or 6 millimeters OD. Since I plan to make my own coils and I live in the USA, I've decided to standardize on 1/4 inch OD soft refrigeration copper tubing. I know that I've said this before, but that's because 1/4 inch tubing and fittings are readily available at most hardware stores and on the internet. This plan has worked out well for coils of inside diameters down to about 1 1/8 inch ID, and again, as I've said before, I can use 1/8 inch or 3/16 tubing to make tinier coils and then build them up to 1/4 inch where they go into the machine. I always water cool my work coils, so all my suggestions relate to water cooled work coils. I learned early on that the method of passing the coil ends over the capacitors, as several of the ZVS induction heaters do, is not good for several reasons. Here we see the coil passing over the capacitors on this 1000 watt unit, and of course when you hook up a cooling water tube, that's going to pass across the capacitors too. First, each time you change coils, you stress the connections from the standoffs on the PC board, which are right here and here. Second, it is often awkward to change the coil because of the coil ends location toward the rear of the PC board, especially if a cooling fan is mounted above the board, which I strongly recommend doing. Third, when changing coils, it is hard to keep water from going onto the PC board if you're having to pull the tubing off of the coil ends while they're in the vicinity of the board here. To avoid this issue, I have moved the connection points for the 1000 watt unit out to the front of the board using 1/4 inch compression fittings. For the 2500 watt unit, I went even further, making brackets to move the connection points to the side. This shows how I connect work coils to my 1000 watt heater using 1/4 inch compression fittings. In this case, the tubing still runs over the capacitors underneath the fan, but of course we're water cooling, so it doesn't become too much of an issue. This shows the work coil connections that I'm currently using on my 2500 watt ZVS induction heater, and if I had it to do over again, I would do the same thing with the 1000 watt. This bulkhead separates the work coil and the heating area effectively from the whole induction heater itself, and as you can see here, the copper tubing coming in from the work coils makes a 90-degree bend so that the cooling water and copper coils never go across the MOSFETs or the capacitors on the system. The cooling water must always flow into the lowest point of the work coil. Make sure that you start, when you're winding a coil, make sure that you start it correctly so the lowest point on the coil, when it is connected to the heater's output and to the cooling source, is connected to the pressure side of the cooling water circuit. This is necessary so the water flows into the bottom of the coil, filling each turn, pushing out all the air ahead of it. I've done this backwards a couple of times with really bad results. If the water flows in from the top, it does not necessarily fill the tube completely. Any air spaces allow heat radiated from the work to quickly heat sections of the coil beyond the boiling point of water, producing tiny pockets of steam, which can force even more water away from contact with the tube walls. I always insulate my work coils. The insulation eliminates the possibility of having the workpiece short out turns of the work coil if you move your work from side to side a little bit. A shorted work coil can quickly destroy MOSFETs and drive components, which certainly ruins your day. A second benefit of insulating the work coil is that the half of the insulation that faces the inside of the coil reflects some heat energy back toward the work. This effect decreases heat loss for the work and keeps the cooling water cooler. This has worked out very well for me. So, should you insulate the tubing before winding the coil or insulate the coil after it has been wound? I've done it both ways. For most of my solenoid type coils, that's, multi-turn, just round ones, as opposed to something like this knife tempering coil. For most of my solenoid type coils, I simply wrap the tubing around cylindrical mandrels of the appropriate size. In this case, it is probably easier to insulate first. And this is an 1.1/8" coil that I just made a little bit ago, and I could have done this one either way easily. But for coil shapes that require the use of tubing benders, the added thickness of the insulation that I use prevents the tubing from properly fitting into the grooves of the bending tool. If you do insulate before forming the coil, don't insulate the tubing where back bends will need to be made. If the insulation is a bit loose on the tube, you can push it back into the coil while back bending occurs with a tool, so the tubing bender will fit on the tube properly. A word about testing coil inductance. If you follow my advice of setting a minimum coil inductance goal of about 0.9 microhenry for the 1000 watt heater, you will want to know if your design meets those criteria or not before trying it out. Note that if you wind the coil before insulating and test the inductance at that time, the reading will change to some small degree after you spread the coil enough to insulate it. After all is said and done, I think it is best to simply hand wind tubing around a simple circular mandrel. The main value of some of these purchase tools for us is for making the 90-degree bends and back bends at the end of the anvil. Thank you for watching.